Hello, everyone. Oops, I'm sorry. Okay. And okay. Okay. We check and see if anyone else is waiting to come in. Okay, I think that might be it for now. So we'll go ahead and get started. Okay, I'm going to share my screen. Okay. All right, for next week, Monday's a holiday. Wednesday is going to be Zoom for everyone. Friday, I have a test scheduled, and it looks like it won't be practical to give that on campus as I originally intended, so that will likely be online, and I'm anticipating that it will cover up through chapter 3, the chapter that we're on right now. Wednesday will be all Zoom, and then reminder that you have a lab report today, so scan it and send it into the grader by email.
Wait, Dr. Trump, I have a question.
Yeah.
At the end of the lab, there is 2 questions. Do I have to answer them?
Okay, the recrystallization lab.
Yeah.
No. Let's see. One of them has to do, I think, with you don't get crystals to form. That means that it's too dilute, and I know some of you experienced that. But no, I'm not going to require you to assign those, or I'm not going to assign those.
Okay, thanks.
Okay, I won't be collecting the pushing electrons, but make sure that you complete chapter 1 by next week, and then after that, I'm going to assign chapter 2, which is actually very important. That's on resonance. And after the first exam, I'm planning to have a quiz over resonance. That's something you're going to be using all throughout the year.
You said you're not going to collect that?
Right, I'm not going to collect it. It's since you're not on campus, it's the details of how I collect that and give it back is complicated. So I'm no longer going to collect those. Okay, so let's go back to, we were looking at cycloalkanes last time. Okay, make sure that you know these alkyl groups. Okay, make sure that you can distinguish, especially among the butyl groups, butyl, isobutyl, sec-butyl, tert-butyl. Okay. We talked about petroleum refining last time. The different components of petroleum, the fractions, are separated by fractional distillation. Cracking is an important process in producing more gasoline. Okay, here are the important fractions in petroleum. We have gas, gasoline, kerosene, diesel fuel, heavy oil, petroleum jelly, and so on. As we're getting successively heavier, more carbons. And more carbons means higher boiling point. Each one of these products is not a pure substance, but a mixture of similar compounds. Okay, I'm going to skip through this. Okay, we talked about conformations. They're not necessarily considered isomers, but they're different forms that are the result of free rotation about a single bond. Okay, here we have eclipsed, and in the middle we have staggered for ethane. This is propane, sorry. And then butane, we have a couple more. We have the gauche, okay, in which the methyl groups are 60 degrees apart. We have eclipsed, totally eclipsed, where the methyls are in the same plane. And then we have anti, where the methyl groups are 180 degrees apart from each other. Totally eclipsed is the least stable, anti is the most stable. Okay, cycloalkanes. Okay, these will contain the prefix cyclo. And last time we went through some of the cycloalkanes. They have very similar properties to alkanes. They're nonpolar, relatively inert. Boiling and melting points depend on molecular weight. Okay, as the molecular weight goes up, so does the boiling and melting point. Okay, for a monosubstituted cycloalkane, we don't need a number. Okay, so this is methyl cyclopentane, this is tert-butyl cycloheptane. Okay, if there's two or more substituents, we use the lowest combination of numbers, and we list the substituents alphabetically. Okay, since ethyl is first in the alphabet, in this case, it's also assigned position number 1. So it's 1-ethyl, 2-methyl cyclobutane. Okay, this one is 1,1,3-trimethyl cyclopentane. Okay, not 1,3,3. We're going to use the lowest combination of numbers. Cycloalkanes can be substituents. Okay, the parent alkane or cycloalkane will end in ane. A substituent will end in YL. Okay, so this is 4-cyclopropyl 3-methyl octane. Okay, cyclopropyl is a substituent, octane is the main chain. Okay, so how do you decide whether a cyclic compound is a substituent or a parent? Okay, it's usually based on which one is larger or whether the cyclic or the open chain is more complex, more substituted. Okay, so for this middle one, hexane is more, we would say it's more complex, it's more substituted, so it would make sense to call this the parent and cyclobutyl as the substituent. Okay, and the last one we would choose the larger ring as the parent. So this is cyclopentyl cyclohexane. All right, cis-trans or geometric isomers. Okay, these cannot be interconverted by conformational changes, by folding. Okay, to go from cis, in which we have both methyls on the same side, both substituents on the same side, to trans, we actually have to break a bond and reform it in a different position. Okay, so these are isomers. They're different compounds. They have different properties. Okay, we talked about the two kinds of strain that can exist in cyclic compounds. The two kinds of strain are torsional strain and angle strain. And there's also a third one, which is called steric strain. Okay, an angle strain, this results when we have a very small ring, such as a 3 or 4 membered ring, in which the angles of the regular polygon, an equilateral triangle or a square, deviate from the ideal of 109.5 for a tetrahedral carbon. Okay, so this introduces strain in the bonds, and it leads to what are called bent bonds. As a result, cyclopropane and cyclobutane are more reactive. They produce a higher heat of combustion than other cycloalkanes. Right, the other type of strain, which is shown here, is torsional strain. When cyclobutane has all 4 carbons in the same plane, you have a square, these hydrogens are eclipsed and their electron clouds will repel each other. We can quantitatively measure stability using heats of combustion, and in order to have a fair comparison, it's for cyclic alkanes, it's heat of combustion per CH2. Okay, I showed you this last time. There is both torsional and bond angle strain, considerable torsional and bond angle strain in cyclopropane. Okay, an equilateral triangle has angles of 60 degrees, which deviates considerably from the ideal of 109.5. The hydrogens have no choice but to be eclipsed. You cannot fold the 3-membered ring. Okay, this is showing the bulging or bent bonds in cyclopropane. Okay, in cyclobutane, some of the strain can be relieved by folding the 4-membered ring. All right, so I'm going to get out a model here. All right, so here is cyclobutane. And I'm going to zoom in just a little bit. Oops, go the other way. Oops. And right, so here is cyclobutane. and we can fold the ring, and that avoids eclipsing. Okay, if you look along this bond right here, the hydrogens are no longer eclipsed. This also relieves some of the angle strain when we fold it. Cyclopentane, most stable arrangement is the envelope. Okay, in which 4 carbons are in the same plane and the 5th is above the plane. This is the flap on the envelope. Okay, in the envelope conformation, hydrogens are no longer eclipsed. Even in the planar conformation, there's not a lot of bond angle strain. A regular pentagon has angles of 108 degrees, but there is torsional strain as a result of eclipsing of hydrogens. Okay, I'm going to go through the chair conformation of cyclohexane once again. One thing we did not cover last time was larger substituents at the axial and equatorial positions, but I'm going to go ahead and review this. Okay, so we draw our chair. Okay, so these are the alternating axial positions. These are the equatorial. Right, the 3 on the right point to the right, the 3 on the left point to the left. These are the equatorial. Right, in the chair, we can see that by the Newman projection, where we're sighting along this bond and this bond, okay, we can see that there's no eclipsing. In the boat, we can see that we do have eclipsing. Right, the boat conformation looks like this, which we have these 4 carbons in the same plane, and then these 2 are above. Okay, so when we look along these 2 bonds, we see that the hydrogens are eclipsed. The CH2 groups, the methylenes, are eclipsed. And you also have a third type of strain. This is called steric strain, where these hydrogens that are not closely bonded to each other, they're on remote carbons, they repel each other. It's called steric strain. The least stable conformation is what's called the twist boat. And okay, talked about this last time, and then I'm going to get into some other substituents. Okay, in methyl cyclohexane, Okay, here we have methyl in the axial position. It's directed straight up. And when methyl is in the equatorial position, let me go back. In the axial position, this methylene group, CH2, is gauche to the methyl. They're 60 degrees apart. In the equatorial position, and all I need to do here is do the ring flip. Okay, where the methyl becomes equatorial. Okay, then the methyl and the methylene are anti to each other. They're 180 degrees apart. And so in there's more room in the equatorial position. A cyclohexane ring with substituents in the equatorial position is more stable, lower energy than when substituents are in the axial position. Okay, when the methyl group is in the axial position, okay, you have what are called 1,3 diaxial interactions. Okay, this is like the steric strain I was talking about a little bit ago with the boat. Okay, 1,3 diaxial. So there's some repulsion going on between the hydrogen on this methyl group and this hydrogen 2 carbons away. Okay, in the equilibrium form in which the methyl is in the equatorial position, we don't have that diaxial interaction. So this is more stable by 7.1 kJs per mole. Okay, so we didn't get to this one last time. So we looked at just one substituent, a methyl. Okay, these are some other substituents. And this is the energy difference between the axial and the equatorial in kJs and kcals per mole. We're going to go mainly by kJs per mole. Okay, it turns out that when we have a fluorine, it's actually a little bit more, just slightly more stable in the axial. Okay, I'm not sure why that is, but it is. But any other substituent, okay, especially chlorine and bromine, which are larger, they're going to prefer the equatorial. Okay, and as the substituents get larger, there's a greater and greater preference for the equatorial. Okay, if we have a tert-butyl group, I'm going to go ahead and make a model of that. We have a tert-butyl group. Okay, in this case, there's a very large difference between equatorial and axial, and this actually effectively locks the ring. It prevents equilibration. Okay, so the tert-butyl, if it can, it has to be in the equatorial. Okay, unless you have another tert-butyl group, which if we have trans 1,3 di tert-butyl, then of course the other tert-butyl would have to be axial, but anything else, tert-butyl group has to be equatorial, and the ring is effectively locked. Even with something like isopropyl, there's a significant difference between axial and equatorial. Equatorial is quite a bit more stable, and even with ethyl. Okay, let's look at cis-1,3-dimethyl cyclohexane. Okay, when both groups are axial, okay, it seems pretty obvious that this is cis, okay, because both methyls are on top. When we do the ring flip, okay, it may be a little bit harder to tell, but this is still cis. Okay, in order to go from cis to trans, we have to break and reform a bond, but we didn't break any bonds, we just folded the ring. But this is cis, okay, because if we compare the hydrogens, for example, they're both axial and they're both straight down and they're both on the same side. Okay, and at equilibrium, we can see that the di-equatorial is much more stable. In fact, it represents 99.9%. Okay, when both groups are axial, okay, what we have is we have a diaxial repulsion between the methyl groups. This is even greater than what we saw earlier with the methyl and the hydrogen. If we have two methyl groups, there's even more steric interaction. Okay, what about trans 1,3-dimethyl cyclohexane? Right, in this case, to go from cis to trans, right, I'm going to leave this one at the methyl position, in the axial position, and then I'm going to take this one on the top and put it on the bottom. Okay, so that's now trans. Okay, in the trans 1,3, we have one axial methyl and one equatorial. Okay, when I do the conformational ring flip, okay, I bring this carbon down and this one up. What was equatorial now becomes axial. What was axial now becomes equatorial. So in both forms, we have one axial, one equatorial. So these have the same energy. And so there's no preference of one for another, unlike the cis. Okay, here is cis-1,4-di-tert-butyl cyclohexane. Right, in this case, because there's so much steric interaction with this axial tert-butyl group. The tert-butyl group is so large, takes up so much space that it actually ends up forcing it into the ring into a twist boat conformation. Okay, but the tert-butyl group on the left remains in the equatorial position. Okay, so this problem involves draw both chair conformations of cis-1,2-dimethyl cyclohexane and determine which conformer is more stable. So let's do that. So here is cyclohexane ring. And cis 1,2-dimethyl. Okay, so for to have both methyl cis, they either need to be both on the bottom, hydrogen's on the top, methyl's on the bottom, hydrogen's on the top, so this is cis, or both on top. Okay, so which one do you think is more stable? Anyone? Okay, they're both the same. They have the same energy. One's axial, one's equatorial. Okay, repeat for the trans isomer. For the trans isomer, okay, this one is on the bottom, this one needs to be on the top. That's trans. And I'll switch these two to make this one trans. Okay, in this case, unlike the cis where we had one axial, one equatorial, in this case, this one has both axial, this one has both equatorial. Okay, so the one with both substituents equatorial will be more stable. Okay, and then let's compare cis and trans. Okay, so this is the solution to the first one. They have the same energy. Okay, one's axial, one's equatorial. For the trans, the higher energy has both axial, the lower energy has both equatorial. And the trans isomer actually is more stable because the most stable conformation is the trans isomer, which is diequatorial. And this is also the much preferred equilibrium structure. Okay, remember that cis and trans are distinct isomers and they can't interconvert by conformational changes. Okay, so the next problem is draw the most stable conformation of trans 1-ethyl 3-methyl cyclohexane. Okay, so the trans 1,3 has one axial, one equatorial group. Okay, and the key idea here is that we want the larger group to be equatorial. Okay, so when ethyl is equatorial and methyl is axial, this one is more stable. And this is the preferred equilibrium structure. All right, and then we'll talk about bicyclic systems. Next. Okay, we'll talk about three different kinds of bicyclic systems. Bicyclic, bridged bicyclic, and spiro. Okay, what we have here is a bicyclic system. And a bicyclic system consists of two rings that share two carbons. Okay, this one is commonly called decalin. Okay, from decane, deca is 10, so it has 10 carbons. And the shared carbons are called bridgehead carbons. Decalin has two geometric isomers. The rings can be cis or trans to each other. The trans is actually more stable. And if you look at the hydrogens here, you can tell that it's trans versus cis. Okay, the cis is sharply folded like this. Okay, so these are what we call fused rings. And bridged rings share two non-adjacent carbon atoms and one more carbon that is a bridge between them. Spirocyclic compounds are rare, and two rings share only one carbon. And I'll give examples of all of these. Okay, so this is how we name bicyclic systems. Okay, so for the first one, you have a 6-membered ring. You have a 6-membered ring that's fused with a 4-membered ring. Okay, where these rings share carbons, these are called the bridgehead carbons. And we call this bicyclo. I'm off screen here. Okay, this is called bicyclo. Right. Then we use square brackets. We start at one bridgehead, and then we go along the largest bridge first. Okay, a bridge is going from one bridgehead to the other. Okay, so in order to go from here to the next bridgehead, we would cross 1, 2, 3, 4. Okay, so the first number is 4. And we separate these with periods, not commas. So 4 period. The next largest ring is this one. So we start from this bridgehead. We go 1, 2. So 4, 2. Bicyclo, we need 3 numbers. And to go this way, we cross no carbons. Okay, so that's bicyclo 4, 2, 0. And then we identify the total number of carbons. Okay, so this would be octane. Bicyclo 420 octane. Okay, we can check this. 4 plus 2 plus 0 plus the 2 bridgeheads adds up to 8. Right, next we'll look at a...
Wait, Dr. Trump.
Yes.
Yeah, sorry. Could you please repeat, how do you get the third number?
I'm sorry, I can't hear you.
How do you get the last number, the third number?
The last number, the 0?
Yeah.
Okay, when I went this way, I crossed 4 carbons. When I went this way, I crossed 2. Then when I went this way, I crossed 0 carbons.
Okay. So the last number is the one in between the bridge. Yeah.
Yeah, the last one is 0. And we go in descending order, largest first and then smallest last. Okay, that's a fused bicyclic, or just bicyclic, it's called.
And it's bicyclic because there's 2 rings, right?
2 rings, right, bicyclic. Okay, this is This is a bridged bicyclic. Bridged means that we have at least one carbon in all three of the rings. So this is bicyclo. Okay, square bracket. Okay, my two bridge heads are here and here. Okay, that's where the two rings join. If I go across this bridge, I cross two carbons. Okay, and then a period. If I go across this one, I cross two carbons. And if I go this way, I cross how many? Okay, I cross one. Okay, and this would be heptane. So that's bicyclo 2,2,1 heptane. Okay, this would be bicyclo 2,2,2. Bicyclo 2,2,2 octane. These are the two bridges. Cross two carbons going this way, cross two carbons going this way, and two carbons going this way. So this is bicyclo square bracket 2,2,2 octane. And again, we can check 2 plus 2 plus 2 is 6, plus 2 for the bridge heads would be 8. Okay, and then I'm going to give a couple examples of spiro. Okay, spiro compounds are where two rings share just one carbon. Right, so that's a spiro. And the way we would name this is spiro, again, square bracket. We go across the largest bridge first. Okay, so that would be 1, 2, 3, 4. Then we go across this bridge, that would be 3. And so this is spiro 4,3 octane. A bicyclo has 3 numbers, even if one of them is a 0. Spiro has 2 numbers, and this number plus the shared carbon should add up to 8, which is octane. Okay, in 3 dimensions, these rings would be twisted. It would actually be perpendicular to each other. I'm going to go ahead and make a model of that for you, and then we'll be just about out of time here. Okay, so here is a 5-membered ring. 4-membered ring. Be like this. Okay, so the 4-membered ring and the 5-membered ring are actually perpendicular to each other. Decalin, if we were to name that systematically, would be bicyclo 4,4,0 decane. Okay, we cross 4 carbons going this way, 4 carbons going this way, and then going this way we cross 0 carbons. So bicyclo 4,4,0 decane. Okay, that is That's all I'm going to go over today. And I will see you on Zoom next Wednesday.
Dr. Trump,
Yes.
so we don't have to answer those questions in lab report?
Right. You won't have to answer the questions.
Perfect. Thank you.
Okay, and the one, let's see, you might have missed it at the first. There was one about why crystals won't form. That's usually because it's too dilute. Okay, and we had a couple groups that experienced that, and you have to boil off some of the water or some of the solvent to get it to crystallize.
Mm-hmm. Yeah. Yeah, I was just wondering if we would have to do that, but thank you.
You're welcome.